All right. All right. Well, hopefully everyone had a good weekend. And now we're back at it. So today is the 7th lecture in this section well, there's only one section. Sorry, I'm so used to that intro. Today is the 7th lecture in 364, and we're going to be talking about optimization, primal optimization, and all sorts of gradient descent nuances that we got introduced to last time, but didn't really formally define. So we're going to basically talk about gradient descent today, and then that's before we'll jump into linear models, linear regression, logistic regression, that sort of thing. Okay, makes sense? All right, so first question. Okay, all right, I think it's working. First question. Why can't I spell? All right. First question. What's primal optimization? So primal optimization is effectively what we have been doing so far. We have a optimization problem. For instance, we have a function that takes in a bunch of inputs. In this case, x is one or more variables. And then we have some constraints we subject it to, some inequality constraints. We could have some equality constraints we subject it to. But the basic idea is that we want to find a minima or maxima of the function, right? We want to find the arguments that provide this function's minimum value, right? So that's what we've been doing, okay? That's exactly what we've been doing. That is the original optimization problem we want to solve. So when people say primal optimization, that's what it is in the name. You're taking a problem in its primal form, in its default state, and you're trying to optimize it, okay? This is in contrast to dual optimization, which tries to reformulate the problem and generate the problem in new methods. Different thing. Nope. Come on. All right. So that's what we mean by primal optimization. This only really comes into play. This term comes into play when you talk about those more advanced methods, namely dual optimization, in your optimization class. I forgot the number is. It's like ECE 490 something. So in that case, you're going to go through primal optimization first, then you're going to go to dual optimization. In this class, we're not going to go into too many optimization techniques, so all you have to know, primal optimization just simply means it's a fancy word for original optimization problem. Okay? Okay, so returning back to the optimization problem, we have a function, and then it's subject to some constraints. And we want to find the smallest value, to find the smallest set of inputs for which this function is minimized, right? So we have, for instance, you have a function. This is represented in 2D space. And you have a saddle point, for instance, somewhere where the gradient is 0, but it's not done decreasing. You have local minimas, and you have a global minima, where it is where it is the smallest that it possibly could be. So this is what we want to find, right? Now, that's what we want to find, but the issue is that finding that global minima is a hard problem. It's a hard problem because it's just a hard problem. Optimization problems, finding a global minima for any given function is a hard problem. And that's why we have to group functions by their characteristics in order to develop new techniques and new methods for optimizing them. Namely, one important property of functions is what's known as convexity. A convex function is a function where the line segment between any 2 points on the graph lies above or on the graph of the function. Okay? So this starts off, so a linear line is still a convex function, but all this means is that when you have a dip, you won't have another dip. Okay? And this is especially important for trying to optimize, because as we see in this graph before, this right here is not a convex function, because if we have a point right here and we have a point right here, then the entire line doesn't lie above or below the graph, right? The issue here is that the function is going up and down, and it makes optimization significantly more difficult compared to a function like this, which simply goes down once and then up, right? It is convex. So why is that important? Well, it's important for reasons that you could prove in your optimization class, but for reasons I'm just going to tell you, it's important because it makes optimization of this function easier in some respects, right? You don't have to necessarily worry about getting stuck in a local minimum versus a global minimum, because in a convex function, every minima is the global minima, and there is only one. There is one global minima. So if a function is convex, that sort of alleviates your worries a lot, right? Because right here, we have local minima, we have global minima. If we do something like gradient descent like we were doing before, and we choose an initial point here, you would follow the gradient and you would fall into this local minima and have no chance of recovering. And what's worse is that you would never really know if the minima you found is local or global. You would never really know if this is the true minima of the function, or if there is a better minima somewhere out there that you should kick yourself and try to find, right? But if you could prove that the function is convex, then when you find the minima, you know you're done, right? So knowing the endpoint is kind of a nice thing. So that's what it means for a function to be convex. The mathematical definition, there we go. The mathematical definition of convexity is that given a function where you have a bunch of real inputs that is mapped to some real number, a function is convex if for all points x and y, if for all points, given 2 points, x and y, then for all parameters of lambda, the following inequality holds. Namely, f of lambda x plus 1 minus lambda y is less than or equal to lambda f of x plus 1 minus lambda f of y. Okay? So, y what does this function mean? Let's look at this inequality. You guys are gonna have to see this, and you're gonna have to read a lot of papers that do all these weird inequalities like this. So it's good practice to try to decipher them. What does this inequality mean in plain terms? Why did I write it like this? Why is it written like this? I didn't write it like this. I copied it from other books. Yeah, please.
Is it something like, well, when you look at both ends of the output, which is like at the, when we look at the graph with both ends of the output,
Yep.
we can see that the things between the domain is like lesser than those 2 points of the output at the left and the right side.
Right. Yeah. So what is that like lambda doing? I think you got it. You got it perfectly. But what's the point of the lambda right there?
It's linearity, but
is it like one end and
Yeah. Yep. So that's so good. So you're defining two ends of the line, right? You're defining a x point, you're defining an x input and a y input. And all we want, all this is saying is that this term right here, lambda x plus 1 minus lambda y, that is somewhere along this interval. This interval is from 0 to lambda, and so if we want an interval between x and y, and we want to adjust, if we want some point between this interval, we adjust lambda to be from 0 to 1. And so what we're saying here is that the function between x and y is this function, the value of this function between x and y is less than or equal to the value of this function at x mixed with the value of this function at y linearly. Right? So that's all it's saying. It's saying that if you draw a straight line between these 2 points, and then you take a point from this straight line, that's what this side is saying. It's saying that this has to be greater than that point for the actual function, the output of that actual function. Right? Yes?
Do we know the value of lambda?
It's for any value of lambda. It has to be true for all values of lambda.
Okay.
Yeah. So you have to. So this is literally saying that for every point along this line, so for every lambda along that line, this property holds true. Less than or equal to. So it could be. So the equal sign is important because it could be a straight line, like linear line. A straight linear line is also convex. So you need that less than or that equal to. But basically, you want to say that if you have a straight line between these 2 points, and then you choose a point right here, this would correspond to some lambda, and then you find the actual function value at that point corresponding to the same lambda, and then you have to make sure this equality holds. You have to make sure the actual function value is less than the straight line you draw between those 2 points. And this is for all inputs, all possible inputs, and all possible lambdas. Okay? And that's how you guarantee if a function is convex. Make sense? Yeah, please.
Wait, so it's like, just to confirm, like
Yeah.
either a straight line or it curves more downwards.
Yeah, yeah, yeah. Downwards is a dangerous term because you have to be a little careful what you mean by it. But yeah, you're effectively right. You're right for now. And then when you go to 400 level courses, they could tell you why. They could give you some counterexamples. All right.
Wait, what are some counterexamples?
Not counterexamples, but just like the term downward is a tricky because when you're dealing with 50 dimensions, right? When you have 50 variables, there's no real thing as downward, right? Yeah, but in a 2D case, you're right. 1D case. Wait, this qualifies as 1D. Yeah. Okay. Yeah. Yes, please.
This is a curiosity thing, but
Yeah.
would it also be accurate to describe it as saying the second derivative is always positive? Would that also define a convex function?
Yeah.
Okay.
Yeah. So yeah, I forgot to include that, but an important other, Colby, right? Yes.
Kobe, yeah.
Kobe. Yeah. Sorry. Kobe's absolutely right. Yeah. Another way to define it: second derivative is always positive, but sometimes derivatives are hard to find also. So that's why this definition appears more often. Okay, makes sense? So, examples of convex functions: exponential, negative logarithm, negative entropy, norms, log, sum, exponential. All those functions are all convex for obvious reasons. Why is negative logarithm? Okay, let me throw out this. Why is negative logarithm convex but not positive logarithm? Yeah, please. Well, that's true too, second derivative, but also a positive logarithm looks like this, right? It's a positive hump, right? So yeah, So it can't be. So it can't be. It can't be convex. Okay. See, easy one. No tricks. Yeah. So same reason for negative entropy. That's the right idea. Examples of non-convex functions. Besides positive logarithm. Yeah, please, Patrick. Yeah, sine, cosine. Periodic functions are never convex. A lot of operations preserve convexity. All the linear functions that we're going to be dealing with in this course, weighted sums, pointwise maxima is also non-convex, are also convex. So I should have. Oh, well, let me adjust this real quick. This was supposed to be on another side. I don't want this to be. There we go. Yeah, okay. So why is convexity important? And I alluded to this. This is actually just like a smattering of importance. There's a lot more reasons why convexity is important besides these. But you have what's known as the global optimality guarantee. If a function is convex, then any local minimum is a guarantee to be a global minima. And that's very, very important, right? That means that that's something that you won't get many times in life. But when you have it, it's super nice because you don't have to worry about trying to train your model to be even better. Once you reach the minima, then you're pretty much done. Well, done with the model, but then you might have to improve the model in some other way. But you're done with training it. So that's a very nice thing. And other more important reason, arguably, for our purposes, is that there are many efficient algorithms for convex problems. Namely, we know we could solve convex problems very well using gradient descent. And then there are other optimization methods such as Newton's method, interpoint methods, simplex and interpoint methods that allow you to solve these problems very easily, right? So knowing that, going back here, so keeping in mind that basically these linear compositions are convex, then it means that linear models are kind of very nice for AI, for us, for optimization, sorry. Linear models are pretty nice for us because it means that we could optimize them and reach a global minima and not really have to worry too much about avoiding local minima or finding new seeds or anything like that. Okay, that's something that is very nice with the small models, and you'll never be this free again after you deal with that, because seeds become important. Okay, makes sense? Okay, so by the way, in this lecture, the major thing in this lecture, I'm introducing you to a bunch of terms because you're going to hear these terms. And I remember when I was first learning this stuff, and I wasn't learning it in school, I was just learning it through internet and by self-teaching. People kept throwing out these terms, and it makes you sort of very confused. So I want to just throw out these terms so that you guys understand what people are talking about, because quite honestly, I think people use like special terms way too much in mathematics and physics. I don't know. Anyway, people don't need to talk in tongues. You could speak plainly. I think Feynman constantly wrote about. If you read his lectures, Feynman constantly wrote about describing describing models in plain language, and I I believe that very much. So that's what I want to do here. Disambiguate most of these terms so that you guys feel comfortable about it. But we won't deal too deeply with these things because this is more of an introductory course. Okay, so now that we have some terms, we discussed some terms, we discussed what primal optimization is, we discussed convexity, why convexity is important. Let's talk about how to find the minimum. And how we find the minimum is something we introduced last week. And we introduced gradient descent, okay? So let's take a step back from gradient descent and abstract the problem a little more because there are many types of descent algorithms. And namely, all these descent algorithms fall under the umbrella of a iterative algorithm, okay? So iterative algorithm is something we introduced last week as well, but let's recap. We have a particular function that we want to find the minimum arguments for. So we start off with some guess for the inputs. And then at that guess, we select a direction and a step size, and then we update the inputs, and we reevaluate. Check whether we should stop, by seeing if the gradient is equal to 0. Gradient is equal to 0 in all directions. Then the probability is that you're in a minima and that you don't really need to do anything further, right? So that's the basic idea. That's the iterative algorithm. Iterative algorithms pretty much have existed since like dawn of logic, okay? That's the basic framework for an iterative algorithm. We have an input, and we need to update it. And we update it by taking a particular direction with all the inputs and taking a step size with each input, okay? So really, the important thing with these algorithms, the important thing to fill out in this iterative skeleton is what direction do we take and what step size should we take? Those are the two major questions in any iterative algorithm. What direction, what step size? Okay, so there we go. So the major thing is, let's start off with the direction. And the major thing with the direction is that we want to make sure that the direction follows opposite of the gradient, right? That's the major point. That's the major thing because we want to minimize the function. So in order to minimize it, we have to make sure that the descent direction goes opposite the way of the gradient, which means that we'll have, for instance, we'll be at a particular point here, and then we have to pick a direction. We have to pick a direction that's opposite of the gradients and follow our way down to a minima, It doesn't necessarily, we won't know if it is a minima, global, if it is a global or local minima, unless we know if the function is convex itself. Let's not assume convexity. But even if we don't assume convexity, the gradient descent seems to work pretty well. This descent algorithm seems to work pretty well. Namely, if we make the direction of the descent equal to the negative of the gradient, right? We saw that last week when we were doing our iterative algorithm. We simply set the gradient. We simply set the descent direction equal to the gradient and just follow and minimize everything that way, right? So this idea of setting the direction of the iterative algorithm equal to the gradient of the function, that has a name. It's called steepest descent. Again, it's like one level down on the taxonomy of algorithms. You have iterative algorithms. And then from iterative algorithms, you have steepest descent. And all the difference is that for steepest descent, we assume that the direction is equal to the gradient of the function that you're optimizing. Okay? Again, people are going to throw around this term. All you need to know is that this term isn't anything important, just means that the descent direction is equal to the gradient. Okay, so there are other directions that you could use. There are other directions that you could use. One popular one is, for instance, scaled gradients, where you adjust the gradient to fall down certain directions faster than other directions. This becomes important later for reasons we'll talk about. But I just wanted to add this in, just so you guys don't think that steepest gradient is the only descent algorithm. There are other descent algorithms, but for the most part, we're going to be focusing on steepest descent. Okay, come on. Okay, so knowing steepest descent, the question becomes, how do we select a step size, right? Because again, we're trying to minimize f. We're trying to find the arguments for which f is minimized, and one option is the exact method. Namely, we take the optimal path. We take the optimal minima every single time. Namely, we have a direction of the descent, and we find the minima of the curve that we take. Okay, we'll come back to this. But what we did last week is take a constant step size. Namely, we chose a learning parameter that is equal to 0.1, 10, whatever. And then we took the descent that way. So steepest descent plus a constant step size is what we call gradient descent. Okay, so that's one level down on the taxonomy. Iterative algorithms are the parent of steepest descent, and steepest descent is a parent of gradient descent. And all this steepest descent means is that direction is equal to the gradient. All gradient descent is that the step size is constant. Okay. So, why are we talking about this? Why are we talking about gradient descent? Because I already went over it. So why should we worry about it anymore? It seems to work pretty well. So why worry about this anymore? And in order to do that, I wanted to show you guys this nice little website. This website was made by Fabian, by a Google AI researcher, Fabian. Oh, I'm going to butcher his name. I'm sorry if he's still watching this recording. Fabian Pedregosa. Yeah, Pedregosa. Okay, Fabian. So this guy is actually the guy, I believe he's the person, he's the head of scikit in Python. So yeah, very well accomplished. Has a ton of citations. I think somewhere on the order of like tens of thousands. So does a lot. But he has a nice little blog here. Highly recommend you check it out. But the important thing is that he has a nice little interactive tool for gradient descent. There we go. So it's a nice little interactive tool. So we see our gradient descent algorithm here, namely we update x according to the previous value of x times the learning rate times the descent direction, which is equal to simply the gradient of the function. So yeah, so there we go. So he wrote this nice little JavaScript viewer. So if we have a function like so, this is a convex function, and it is nice because it is relatively circular. It is relatively equal along both dimensions. We have any possible starting point here and possible starting point, and then we could vary the step size. So depending on the step size, we usually find a very, very strong optimal solution, a strong solution to the optima with not too many wasted steps, right? So all we really have to do here is make sure the step size is reasonably small, right? But not too small. So if the step size is too small, we're going to be waiting all day, right? But and we probably won't get there. But if the step size is too big, oh no, oh no, something, it becomes unstable, right? So the instability, why is the instability occurring? Oh, please. Yeah. I mean, well, yeah, the step size is too large, so it's overshooting the minimum effectively, right? It's going past this point. Maybe I could, oh, I wish this was, well, okay, yeah, right here. Right here, you can see it goes down somewhere here, and then it takes another step, and then it shoots way past the minima, goes up here, and then takes another step, shoots past the minima, up here, and then oscillates back down to get to the step size, right? And of course, if the step size is too big, then it will never find its way back to the minima. It will just sort of be unstable forever and just go out of control. Okay, and finding the maximum step size where for a particular function is a very interesting problem. I think it's one of the first homeworks in the optimization lab. Anyway, in the optimization course. So that's good, right? So in this case, gradient descent seems to be working great, right? You have a starting point, regardless of the starting point, it just, no issues. There's surprisingly tolerant. The step size is surprisingly tolerant for the value of the step size. Everything is working well, right? So gradient descent seems great right now. Now we come to a function, and this is the classic hello world, why we need smart optimizers. So we come to a function where the two dimensions are scaled differently, scaled significantly differently. So we have a function right here that is increasing sharply. So this is a parabola, maybe this is x to the 4. And then you have a function along this axis that is increasing less rapidly, more slowly. Let's say slowly. Okay, and so maybe this is x squared. So you have something along this dimension that's something like x to the 4, x to the 8. You have something along this dimension that's x squared. And so we have a mismatch between what's known as the principal axes of this dimension. This whole gradient is elliptical. It's long in one dimension, right? So now, here's the deal. What will gradient descent do in this case? Gradient descent, when we start off, regardless of where we start it, gradient descent will follow the direction of the steepest curve, right? So in this case, let's start it off right there. The direction of the steepest curve is along the y-axis. So of course, it's going to follow the y-axis down to the slowly decreasing axis, right? So immediately what gradient descent does, it starts off at this point, and it's like we need to descend greatly along the y-axis, and then it will get to the x-axis, and it will slowly make its way to the optimum. And in fact, if the step size is too small, it'll have a hard time making it there in a reasonable amount of time. So you have to increase the step size, and finally you'll get to the optimum, right? But if we increase the step size too much, then we got a new problem. The new problem we got is that we start off this point, and we know the descent direction, right? The descent direction is still good, but if the step size is too big, then we're going to overshoot the minima, right? And then we're going to oscillate along the y-axis while we spend time trying to get to the optimum. Okay, so that isn't good either. That isn't good either because it leads to a lot of unstable behavior. I mean, it leads to just a terrible step size because even at this point, look at this point, we still, even when the learning rate, even when the step size is 0.01, we're still not able to reach the optima. So we have to keep increasing the step size, but there is a very small window for which we reach the optima and also achieve, and also where we reach optima, and we also have semi-stable behavior, right? And in fact, if we go a little bit past that, then we just have full-on madness, and we never reach the minimum, right? So it makes this very finicky, right? Even if we're willing to tolerate the oscillations, this isn't a large range, right? This isn't a large range. You're going to have to guess correctly when you set up your program for this case. So this isn't optimal, right? So that's an issue with the gradient descent. And also this issue exists with non-convex functions also. Like we have a function right here. We know it's non-convex because if we draw a line from here to here, it's not always decreasing, all right? The good news is that gradient descent works even with non-convex functions, right? That's the good news. And it's a wonderful thing. It's a wonderful thing that you have an optimization algorithm that doesn't depend on convexity. You have that we should be grateful for. On the other hand, it sort of sucks it sort of is very finicky. So again, we have a step size. And with this start point, we need to increase the step size a fair bit in order to just reach the optima. But the issue is that when we increase the step size too much, we just go crazy. And in fact, we get unstable behavior, and Fabian's JavaScript applet breaks. Right? It's just a little bit unstable, and everything goes to hell. Right? So this illustrates two important points. One, it illustrates the first important point is that choosing the correct step size, making it a fixed point isn't optimal. Okay, we do it a lot. I do it a lot just to get something working, but it's not something that you do when you're working with more advanced models, and that's why we're going to discuss more advanced step sizes, more advanced optimization techniques, especially, I want to say 3 weeks down the line. We're going to be discussing some more advanced. We're going to be discussing what the PyTorch default optimizers do. The other thing is that hopefully this shows you why. This is a good visual demonstration of why convexity is important, right? Because you get because non-convexity pretty much invites unstable behavior, and that's not good for anyone. So yeah, all that makes sense? Okay. I highly recommend you check out his website. Yeah, he has a lot of notes on optimization. He has a lot of blog posts on optimizations. Was it this one I was looking for? Okay, I can't find it. I'll come back. You guys should check it out yourself. A lot of good articles. Okay, we're going to come back to these for his website. But so we have the constant step size that we were using, and by all means, I don't want to crap on like anyone for using it. Listen, it's constant step size. It's a very, very good, quick and dirty way to get something working. And a lot of times in computer science, that's step one. Just get something working. Okay. So you should always try to go for the constant step size first. Now, if you want to get something working well, if you want to iterate on it and get it working well, then you have to focus on trying other step sizes, other methods, other more adaptive step size choices. And so we're going to discuss one of them today, and then we'll discuss one of them today, and then when we discuss PyTorch optimizers, we'll discuss more adaptive step size stuff later on. Okay, so step size. So choosing a constant step size isn't ideal. But, so what can we do to find the ideal step size? Oops. have to jump around between editors. That's what I get. Okay, so what should we do to find the ideal step size? Well, let's think of the problem one more time. Okay, we have a particular optimization problem, and we have the direction, right? We have the direction that we want to descend down. Okay, we have the direction. We have the current value of the inputs that we have, right? So we have the current value of the inputs. We have the direction that we need to go. The only question is how far along that direction should we go down, right? Now, we did constant step size because it's computationally inexpensive and easy to code up. But if we are feeling up for it, we could choose something more advanced. Namely, we could look down, we could see the direction, and we look down that line, right? And if we look down that line, we'll see a parabola. We'll see a descent, and then we'll see probably an increase later on, right? So if we look down the descent direction, we see that there is an optimal point somewhere down this direction that we need to step to. That will minimize the overall function. Okay? So let's just do that. Let's just look down the descent direction, have a bit of foresight. We don't have to take a single step. We could just search down the line for the optimal point, the optimal step size to take at this point in order to minimize the function. And so this is the idea behind optimal line search. Okay? Optimal line search isn't necessarily an algorithm itself, but it is a concept. It is the idea that when you need to take a step, you might as well just take the best step, right? Spend a little extra energy looking to see what the best next step is, and then take it, right? So that's a good idea. Well, I mean, it is an idea. It's like your friend saying, oh, all you need to do is just do it. I mean, awesome, but it's not super helpful in that moment. It is a good idea. Of course, all we need to do is take the optimal step. The question is, how do we take that optimal step? So how you take this optimal step, there's a whole bunch of algorithms dedicated to this. So many algorithms dedicated to this. But the major thing is that you have to weigh the complexity of finding this optimal step against the time you take to compute, like the computing time, right? Because we're training models are getting bigger. Every second you spend searching for the optimal step is a second you're spending not updating values. If each iteration takes 1 millisecond, but calculating this step takes 100 milliseconds, you could have taken 100 steps in the time you took to calculate this optimal step, right? So you have to find that balance. The major thing is that any function that tries to give you the optimal step basically has to find that balance between computation time and the time that you're actually using to take the optimal step. So many algorithms behind this, but by far the most popular the most popular step size, the most popular adaptive step size algorithm is something known as Armijo's rule. Okay, so Armijo's rule for machine learning is, come on, formatting's everywhere today. Armijo's rule is for machine learning is simply that the step size is simply that you start off with the initial step size, and then you have a condition. You have a condition, and as long as the condition holds true, you don't update the step size. You start off with a big step size, As long as the particular, you have a condition for which you don't, so which you hold to, and as long as the condition holds true, you keep that step size big and you keep going big down. Now, if the condition does not hold true, we decay the step size, okay? We cut it in half. I mean, cutting it in half is pretty much all I've seen, but you could choose a different decay variable also. I've seen actually I've seen 0.9 also, if you want to decay slowly. But every time, if the condition does not hold true, then we decay the step size, and we repeat until we find the minimum or until a better step size is found. Okay? So we've done this too, right? We've done this too in our iterative algorithm where we decayed the step size, although not with gradient descent. We did sort of a decayed step size just right off the bat. But this is basically everyone has done this, right? This is the basic idea behind binary search. You know, you start off with a big thing, then you break it down into small things, small things, small things until you find the solution you're looking for. Same idea. So the question is, what is the condition? That's important here. What's the condition? And the condition simply states that the difference between the function after you take the step and the function before you take the step is less than or equal to some fitting parameter times the gradient times the descent direction. Okay? You want this step, the difference in this step to be below a certain value that is proportional to the function and that is proportional to the current step size and that's proportional to some fitting factor sigma. Okay? So why is this condition so important? So why this condition? This condition follows from a Taylor expansion of the this condition. The way people explain it, I think this is pretty intuitive. I don't think it really necessitates an explanation. But the way people explain it is that this follows from basically a Taylor expansion of the function, namely that if we take the derivative of this function, then we have to take this point plus the first derivative, and then the second and third derivatives pretty much fall off. And so you're left with, you have the derivative of this function, you have this function is equal to f of w plus the descent, and then you put this term on the left, you get this, and then you get the actual descent value. Okay? And then you add in sigma, which is a fitting parameter that controls how much decrease that you're willing to tolerate. Okay, so basically, you want to tolerate only so much decrease. You don't want to tolerate, you basically are bounding. So you're bounding the decrease because on the right-hand side, you're bounding the decrease on the right-hand side. And on the left-hand side, you are ensuring a sufficient decrease by basically saying as long as you're basically saying that you could be as large as you want, and in fact, you want the step size to be fairly large. You want it to be almost exactly this value, so you want to keep the step size large as long as the step size doesn't get too large. Okay? That's the idea. You want the step size to be large, so you keep alpha large as long as possible, but you don't want the step size to get insane. You don't want it to get too large, which is why you have this bounding condition on the right-hand side to keep things stable, and namely to decrease the step size when the descent is getting too large. Does that make sense? So this is literally what we've been doing, right? I hope this doesn't seem as surprising to you. I know every single one of you have probably done something like this before, but it's just taking two very important things, namely decreasing the step size, decaying the step size at every interval if needed, and bounding the step size according to some predetermined criteria. Okay? So going back to Fabian's amazing JavaScript visualizer, he implements Armijo's rule also, basically bounds the step size, and yep, and then here he's using gamma instead of alpha, but same idea. If this condition is held, then we don't need to do anything. If the condition is not held, then we decrease the step size by decay of 0.05. And so, what happens? Well, ideally, so on the normal circumstances, like, when you have a well-behaved convex function, that's our control, everything looks good, right? We see the step sizes, they're all roughly equivalent, and then we see that at a certain point, the step size decreases significantly. I think it's at that point. It's hard to visualize. Yeah, at that point, you can see the step size basically decreases significantly, and so everything behaves as normal gradient descent, which is exactly what we want, right? We don't want this to change. This is perfect. And so doing things this way pretty much maintains that. Now, if we have this, now we have the case where one axis grows significantly faster than the other. And what happens in this case? Well, we could actually see the break. We start off, we do the same exact thing. We descend along the steepest axis, right? Steepest descent. We can't really escape it. It's just going to go down the steepest axis and not really pay attention to other axes for the moment. But that's okay. Step size is large. We get to that other axis, fine. Now, here, what do? Step size is maintained pretty large. And it keeps going until you break, until you find a case where where your step size is going to be too large, and then you decrease it by a half, and then you take another bunch of step sizes. Then you violate Armijo's condition again. You decrease your step size by a half, so on until you reach the optimum. Okay, and this is kind of important because remember where we started out at. With just normal classic gradient descent, oh, there we go. We couldn't reach the optima without this unstable behavior, right? Not good, because we had to make the step size so large, because we had to make the step size large enough so that in this case, so that along here, we could actually reach the optimum eventually in the number of iterations we had. But because the step size was so big, we would overshoot this axis and have oscillatory behavior. Here, we're not doing that. Okay, here, we're choosing a very nice, large step size. But when we need to, we're decreasing the step size and then moving on. We're decreasing the step size and moving on, right? And then as we go on, if we're maintaining a large step size, and then at a certain point, bam, we decay the step size, and keep going until we reach the optimum there, okay? And what's important is, what's more fascinating is that the same thing happens with non-convex functions also. You have an initial large step size that you use to descend along the long gradients. But now that you have sort of the banana gradients, I don't know what it's called, this axis right here, we keep the large step size until we violate the condition, and then we decrease the step size by a half until we reach a solution there. Okay? So, works pretty well, right? So in practice, this step size, adjusting the step size, decaying it after you violate a particular condition, it works very, very well. And because I feel like they add these explanations after they find something that works well. I don't think it's like a mathematical truth that this works well because it's modeled after the Taylor series. I think it works well because you're using a good bound with a decaying step size. But this isn't the only bounds that people have proposed. This isn't the only decaying that people have proposed. So we'll go into more advanced method later. But this is sort of the step one on improving your step size. Yep.
I also want to just like confirm, like step size is just like learning rate?
Yeah, step size is learning rate. Yep. Yep. Exactly. Yeah, you say step size because in convex optimization, I mean in optimization algorithm. So optimization is part of mathematics, right? So mathematics isn't just dealing with machine learning; it's dealing with all sorts of other optimization problems. So that's why they use the term step size. But yeah. Okay, good. Everyone good? Any more questions? Okay, so last little bit. So momentum and gradient descent. So momentum is another key improvement on gradient descent. And one issue with gradient descent, and actually let me jump back to this. Let me jump back here, and let's go back to the normal gradient descent and see that one issue people have pointed out, and like you guys have definitely see, is that gradient descent has no real memory, right? You go left, oops, sorry. You have a gradient, you have a start point, and then it says go down, and you go down. And then you get to a next point. Then it says go up, you go up. Then it says go down, and so on and so forth, right? This is a memory-less system, and part of what's causing this instability is the lack of memory, right? It's the lack of inertia. If this had some sort of inertia, basically, if we weren't able to switch on a dime so much, if we were, for instance, we go down, and instead of immediately going back up, we sort of, because we're changing the momentum, we go up only less than we expect, then we would have less of oscillatory behavior, right? That's something that we notice, like, you know, in physics when we're doing physics 1 in high school. That momentum helps dampen oscillatory behavior, right? So how does that help us? Well, I mean, I just explained how it helps us here, but how can we implement that in our actual algorithm, right? Oh, and by the way, by the way, the case, oh, never mind. I actually forgot what I was going to say. But so this issue is especially bad. Oh, this issue is especially bad when the dimensions are uneven, because again, with the uneven dimensions, we immediately go down the steepest axis, and then we have to make the step size great, and then we have to change back and forth, and that's where the oscillatory behavior comes from, right? So we have contour plot, which it would be nice if it was a little larger, and it would be nice if it was actually centered. Thank you, HTML, for not doing what I want. All right. So we have a particular contour plot, and we have this oscillatory behavior, and namely, we have this uneven contours, these ellipses, okay? So we're not going to get too much into this, but the idea known as condition numbers, okay? And what you could prove if we were actually inclined to do that in this course. I don't know if you guys really want to go through proofs. I would be happy to do that for you. But without going through the proofs, there's an idea in optimization where you have two principal axes, and one principal axis is longer than the other. Okay, there are mathematical ways to measure how long the principal axes are, but the ratio of the principal axes squared is what's known as the condition number. Okay, so you could think of the condition number as just how oval your contours are. Okay, so there's an idea in optimization that you could prove that in order to get within some distance of the minima, you need at least the condition number times log of 1 over e. That's the distance from the minima, iterations to get to that minima. Okay, so the idea is that the larger the condition number, the more oval, the more squished one dimension is, the more iterations you'll need to get to an optima. Okay, so yeah, that sucks. Also, that does mean that if the condition number, for instance, was 1, if the two axes were equal, you would only need one iteration to get to the optimal point. Why? Why, if everything was perfectly circular, would you only need one iteration to get to the optimal point? Yeah, please.
You just take like the first gradient, because if everything's perfect, everything's just pointing directly to the second.
Yeah, exactly. If this is perfectly circular, Dominic? Yeah, Dominic. Thank you. Yeah. So as Dominic correctly pointed out, if everything is perfectly circular, then we know the descent direction will point towards the minima. So if we know the descent direction points perfectly towards minima, we don't even really need to take steps. We just look down the descent direction and find and just go to and find the minima along the descent direction, right? And then we'll only need to take one step. The reason that we need to take multiple steps is that when things aren't perfectly circular, then we aren't looking down towards the minima. We're looking somewhere away from the minima, and that's why you will need multiple iterations to get to that, to get there. Okay? Okay, so I thought this is like a neat little thing. So condition number, so remember, condition number, again, if anyone tries to throw fancy terms at you, don't be fooled. These are very simple ideas. Okay, so as I said before, momentum might help us in this case. So, no, okay. Sorry, I made the slide too big. So, gradient descent with momentum is just a variation on the gradient descent algorithm that basically we have this term that we've been using for so long, namely, we have the actual descent, the learning rate or step size times the actual direction. Makes sense. But with momentum, we actually include a velocity term v of k. And this velocity term helps us keeps the momentum going in the direction that you were going the previous step, right? So we were going in some particular direction in the previous step. We were going at some particular velocity in the previous step. So when we want to make a new step. When we want to make a new step size, we take the gradients, right? We take the gradients, but we also take the velocity of the previous step times some beta, times some momentum coefficient, which again, I've seen 0.9 a lot, but you could adjust it as you want. So we take the momentum, and then we add those things together. Okay, so if we look on our previous graph here, we start off here, and then going and taking this step, we take the step based off the gradient, right? But we also have some sort of velocity here. So now, at our next step, we have some velocity from this previous step going this way, and then we have the gradient pulling us in the other direction. So the average, so these two things get added together, and we don't actually go down here. We'll only go down less far, right? And same thing also, that we have, when we go down less far, we'll have a velocity that's still going this way, but we also have a gradient that's pushing us this way, so we'll go down less, okay? So what's this velocity term doing? All the velocity term is doing is basically making us continue along the direction that we were moving with before, which, if our gradient was stable, if this was perfectly circular and we were going very, very carefully, actually, which if our gradient was very stable and we were going in a very careful manner down towards the minimum, the velocity wouldn't really do anything. it might actually make things go faster towards the minimum, right? It'll actually give a boost to the gradient. So in this case, velocity is a great thing. But in this case, then we increase, when we want to turn on a dime, namely at this point when we want to turn on a dime, we still have a velocity from the previous term going down, and then we have a gradient that's telling you to go up, so that you won't go all the way back up to this point. You'll go back up to somewhere down, somewhere less, okay, and so on. Okay, so the velocity is helping hamper oscillations. Okay. Sorry, it's driving me nuts. There we go. So the velocity is helping us just dampen some of the oscillations, and the learning rate is still doing what the learning rate is doing, as it was before. Okay. So why this works? People love to come up with explanations. There's a whole thing about momentum of a ball rolling down a hill. I don't think that's particularly relevant. I don't think that really a lot of this matches a physical system very well. But what is interesting, what I think an interesting point that people bring up with this momentum is that the velocity is that using this velocity term, it allows you to accumulate the effects of past gradients, right? Because the first velocity is dependent on the first, or the kth velocity is dependent on the gradient of the k minus 1 value, right? So you have this progressive term that's recording the effects, that's adding the effects of all the previous gradients to your new gradient. And I think that's part of the reason why this works so well, is that you're accumulating the effects of all the also being computationally efficient. Okay, that's always the most important thing, is that do things in a computationally efficient manner. You could always keep a list of all the past gradients, but your memory would run out. But in this way, because you are simply adding the past velocities, and those past velocities are dependent on other past velocities and past gradients, you are in effect collecting the effects of all the past gradients, and it's helping smooth out your trajectory. And I guess we covered smooth updates, accelerating convergence, and accelerating convergence, and reducing oscillations. Good. So in order to and as an example, I should have had that on a separate slide. Actually, well, there we go. I forgot I could do that, to have two things side by side. Oh, yes. Okay, so this is gradient descent with and without momentum. So as you see here, okay, no more. So we have the gradient descent without momentum. That's the red line. We see it behave as we saw before, that it goes down to the smaller axis, and then it just slowly hits the minimum, and then it slowly goes to minima. The one with momentum, basically, it starts off going the same direction, but when it gets to this inflection point, the velocity kicks it up, and then it sort of keeps going. The velocity accumulates, and then you get a much faster trajectory to the minima. Okay, that's when the learning rate is 0.02. That's when the learning rate is 0.02 and the momentum is 0.09. I kept that constant. And we could look at how things behave if the learning rate is too high, because remember, one of the issues with just plain gradient is that the learning rates, the interval of learning rate where the thing was small, right? But it turns out with momentum, you have, I mean, with normal gradient descent, when the learning rate is too high, you get these oscillatory behaviors and you get something that won't converge or will converge very, very, very slowly, if at all. But with the momentum, you get something, again, you get this behavior where even though the learning rate is high, the velocity factor is helping dampen out the oscillations. And so because of that, because the velocity is helping dampen out the oscillations get bigger. The oscillations get bigger in one axis directions, but it also helps the variables get to their optimal point. Okay, so I think it's a cool visual to see how momentum helps get the values to a optimal point. And I include you didn't have well. I included the code here, the code to make the animations here. I didn't want to put it in the slide because it's stupid long. But it's really not complicated at all. All of this is boilerplate. So you could play around with the actual loss function and the momentum and learning rate parameters if you want to see what will happen. And you can make it better. Let me know if you make the visualization better, because this isn't my best work, but it's not too bad. So can't be too down on it. Okay. Okay, so that's it for today. And then next time we're going to discuss linear regression, and yeah, and then that'll be that. Thanks for coming today, guys.
I have one quick question on the homework.
Yeah.